In this video, we are going to define the so-called complex amplitude. The complex amplitude is a very important tool to work with sinusoidal signals. So this is a complex representation of sinusoidal signals. Here I put the well-known equation of a sinusoidal signal, and for this signal, now I am going to define a complex time function. So this is a time function, but this time function is complex and it is defined on the complex plane. That's why I am going to put u bar, and this is the notation of the complex numbers and the complex functions, u bar. Next, we are going to get a graphical representation of the sinusoidal signal. First, this is the complex plane. As you can see, on the complex plane, there is a real axis. This is the horizontal axis. And the perpendicular axis is the so-called imaginary axis. And then I put a red circle, and this red circle will be important in the followings. So this is the complex plane. The red circle, the radius of the red circle is equal to u hat, so the amplitude of the signal. So this maximum value is u hat, this will be minus u hat. In this time function it's also u hat and minus u hat. So as you can see, we are going to draw two time functions from the complex representation from the complex plane. So next we are going to define the so-called phasor, or we can say complex phasor. Phasor is a complex vector. So it's a new word. We are going to use phasor many times, and remember, phasor is a complex vector. But how can we get the complex representation u bar of t? This will be a rotating phasor, and the rotation speed is omega. Omega is the angular frequency of the function. So let's say alpha is equal to 0 for simplicity. So in this case, alpha will be 0. So when the time is equal to 0, our u bar t is pointing from the origin to here. So the real axis projection has maximum value, and the imaginary axis projection has 0 value. So that's why I am going to put 0 to here, and I am going to put a maximum value to here. So I mean this point and this point, if you cannot see. So next, let us imagine that the time is increasing a little, and our complex function is pointing to here. So we have got a projection to the imaginary axis, and I can help with this ruler. So it is going to point to here. This is the value. So it's quite easy to get this time now, because this angle is equal to 30 degrees for simplicity again. What is the value of the projection to the real axis? The projection to the real axis is this one. I'm going to put a note here. So let's say the time is increasing again a little, and we are going to go to the 60 degree value, and the projection to the imaginary axis is this value, and the projection to the real axis is this value. Next, okay, the phasor is here. Next, the phasor is pointing to the 90 degree, so along the imaginary axis. In this case, the maximum value is appearing here, but the zero value is appearing here. And from this point, everybody can check that here we are going to get a sinusoidal signal like this one, if you follow the projection of the vector. And here we are going to get a cosine function. So it's a sinusoid, and it's a cosine function. So if you have a rotating phasor, the projection along the imaginary axis will be a sinusoidal function, and the projection along the real axis will be a cosine function. So there are two possibilities. Represent the sinusoidal function with sinusoids, or represent the sinusoidal function with cosine function. It's the same, only there is a phase shift between them. So it doesn't matter which you use, the sinusoid or the cosine function. There are many books using the sinusoid, and there are many books using the cosine function. In this lecture, in Europe, we are using the cosine function for that. So let's say the u of t is u hat cosine omega t plus alpha. So in the graphical representation, I used alpha equal to 0, but it doesn't matter. Okay, we can imagine that. I need more space. We can imagine that it is equal to the real part of u hat cosine of omega t plus alpha, of course, plus j u hat sinus omega t plus alpha. So we can see that they are the same. So if we have got this is the complex time function. So if we have got a complex time function and we get the real part of it, this is the cosine function. So in the parentheses, we can have u bar of t. In the parentheses, there is the u bar of t. Next, we are going to get a new representation of this, because it is the same as the Euler form u hat e to the power of j omega t plus alpha. This is the Euler form of a complex number. Next, we are going to write the following. U hat, the second part is equal to e to the power of j omega t multiplied by e to the power of j alpha. And from the last lecture, we can conclude that this part is not very important from the complex amplitude point of view, because the complex amplitude contains the amplitude and the phase shift. So the complex amplitude is an amplitude. That's why I am going to put the hat. And this is a complex representation, so we need the bar. So this is u bar and hat. It is equal to u hat e to the power of j alpha. This complex number is the so-called complex amplitude. The complex amplitude has two important things. The first is the amplitude, the u hat, and the phase shift, this is the alpha. So there are two informations inside the complex amplitude. But what about power of j omega t. I'm going to draw it with red. So e to the power of j omega t is a very important phasor. So this is the complex plane, imaginary axis, real axis. And e to the power of j omega t is a rotating unit vector. So if t is equal to 0, this is pointing to here. And if the t is increasing, this phasor is rotating, and the rotating speed is omega. So this is a to the power of j omega t. And the radius is equal to 1 because it is 1 multiplied by e to the power of j omega t. So the amplitude of this phasor is equal to 1, but the other part, this one, the complex phasor, containing the amplitude and the phasor. E to the power of j omega t is containing the time function behavior of this rotating vector. So how to use it? How to use it? So from this point, if you have a sinusoidal signal, you can forget it is a time function, but you have to get the complex amplitude, this representation of this time function. This will be the complex amplitude. The complex amplitude is a complex number, and we can work with complex number instead of time functions. So this is the typical view of the calculations. You have got a stable linear and time invariant system. The input is a sinusoidal function, and the output is also a sinusoidal function. So if we have got such a problem, first we have to obtain u bar and hat. This will be u bar, so u hat, e to the power of j alpha. So we have to put the amplitude and the phase to this complex number, and we can forget omega and t for a moment. So it means that our output will also be a complex number. We are going to use the complex amplitude. This will have y and hat and e to the power of j beta. Please don't forget that omega will be the same. So the omega t term will be the same in the output function. So this one. But our question now is how to get y bar and hat from u bar and hat and from the model of the stable linear and time invariant system. This will be in the focus in the next lecture, and in that case we are going to use omega, and omega will be appeared here inside the system somehow. And this is what we are going to talk about in the next lecture.